Okay, so here's f of z given by this expression, and f has poles exactly at the places where the denominator is 0 and where the numerator doesn't kind of cancel it out in any way. So the denominator is 0 when z is 1, and the order of the pole will just be the multiplicity of the 0 of the denominator. So each one of these factors has a factor of z minus 1 in it, so we can factor it as z minus 1 cubed, and we might as well factor the rest for when we do this for the other poles. And this piece will have a z plus 1 factor, but this will also have a z plus 1 factor. And then we have I and minus I are also roots of the last piece. So the bottom looks like this, except maybe I have it kind of off by a sign because the coefficient of the top power of z should be negative, but that's not so important for finding the order of poles. But in any case, we see that 1 has a pole of order 3, minus 1 has a pole of order 2, I and minus I both have poles of order 1. And we could go through and compute principal parts at these poles, but this function's maybe a little too complicated to do by hand, so let's do a simpler one, a little simpler version. Let's say g is 1 over 1 minus z times 1 over 1 minus z squared, and let's try to find the principal parts and the residues at the two poles, which will be z equals 1, which it has a pole of order 2, and z equals minus 1, where there's a pole of order 1. Okay, so let's look at the hard one first. Z equals 1. Let's see, so g factors as 1 over z minus 1 squared times 1 over z plus 1. And I'm going to factor this piece out and then write what's left as a power series involving z minus 1. So to do that, I guess I would need its value at 1, which is 1/2, and then its derivative at 1, which turns out to be minus 1/4. So this is just the derivative of this thing evaluated at 1. Gives me the minus 1/4 here. And that's all I actually need to know to find the principal part, because when I multiply this power series out times 1 over z minus 1 squared, well, I'll get a term with a negative 2 power on z minus 1, and then a term with a negative 1 power, but then I'll get into the constant term and the term of order 1 and so on. And so this is the principal part of g at the pole at z equals 1. Okay, and the residue is the coefficient of the first negative power, so it's this minus 1/4. Okay, let's do the principal part at the pole of order 1, which is at z equals minus 1. So we'll factor this in a similar way, but paying attention to z equals minus 1. So we have 1 over z plus 1, and then this thing here, which is analytic at 1. And so since we only have a pole of order 1, there's not much you need to do. You just need to know its value at z equals minus 1, which happens to be 1/4. Then after that, you'll have higher order terms, which won't influence the principal part because I won't get negative powers anymore. So the principal part is just this one term of 1/4 times 1 over z plus 1. and the residue is just the coefficient of this power, which happens to be 1/4. And again, this residue may seem like a random thing to compute, but it's actually quite natural and plays an important role later. Okay, there is something I'd like to point out further about this example. Let's examine G minus the sum of these principal parts that we found. So if you take G minus the sum of the principal parts that we found at Z equals 1 and Z equals -1, well, you get rid of all the poles because the principal parts will be analytic everywhere except at the singularity in question. So by subtracting away the principal parts, you get rid of the poles. So G minus the sum of these principal parts will be a rational function that has no poles, and, well, this is a special property of G and the principal parts, that they go to 0 as Z goes to infinity. So a rational function with no poles has to be just a polynomial, and the reason is you would write it as P over Q, but by the fundamental theorem of algebra, if you cancel common factors, Q would have to have some zeros that P doesn't have. So we would just have a polynomial. And for a polynomial to go to 0 as Z goes to infinity, the polynomial itself has to be 0. So this says that G equals its sum of principal parts. And so G is written this way. And this is what we call the partial fractions decomposition that you learn in calculus. And so here's the statement. So this example was special in that it went to 0 as Z goes to infinity. In general, you'll have this extra polynomial piece. But there's not too much, the argument doesn't change too much in general. So partial fractions decomposition theorem says that every rational function f, written as P over Q, where P and Q have no common zeros, is equal to the sum of its principal parts and a polynomial. And again, the reason is if you subtract away all of the principal parts at all of the poles, which there'll be finitely many, well, you'll get a rational function with no poles, and that has to be a polynomial. On the next slide, we're going to define meromorphic functions, which are basically analytic functions with possible singularities, which are at worst poles.